Okay, today we're going to try to do some exhaustive pattern matching. Um, well, we're not going to be trying to do any pattern matching, but we're going to be trying to make our compiler encourage our users to do exhaustive pattern matching. So exhaustive pattern matching is when the compiler is able to know that a case is unhandled, really. Pattern matching is really just handling cases. An unhandled case is, yeah, when you don't handle that shape. And pattern matching is really all about the shape of data. So let me show you what I'm talking about maybe with an example. So I think we'll spin up a new file here. And we'll start off by returning 0. We'll just call this exhaustive.k1 and we'll hello exhaustiveness. Start off with a little hello world. Okay, so we just compiled our program and we ran it. We can now look at our hello exhaustiveness program, and it's LVMIR in here. Okay, so let's make a type that we'd like to match on. Actually, let's just start with some built-in types to keep things easy. So best thing we could do is say we have a bool, right? The simplest thing we could do, I'd say, and then when is how we match in this language. So we would say when b and true, we're going to print true. And false, we're going to false. And the idea is that if we leave this case out, we'll get a warning. So let's start. Let's move this into a function called match bool. Does not return anything. And so now what we'll do, we will match bool. We'll print hello world at the beginning, and let's see what we get. Let's see here, a parse error. You know, I'm really unsure what the issue is here. I think these are both valid patterns. I don't think I need a comma here. Well, let's try handling only true. See, we get a match error after hello exhaustiveness. Is there a really small chance that I didn't even implement the pattern false? So for matching, just forgetting my pattern matching syntax. When okay, is it that we need a block? I don't think we, oh, maybe we do. Let's just make sure that we've got both Boolean cases handled here. Ah. Literal bool, B. Okay. I guess I could have introduced a parsing error recently, in which case I might have to pause this recording and figure out what in the world is going on. You know, Oh, okay, so these do go here. Maybe we don't need those. So there's a little syntax misadventure for you. All right, so we're here. So we passed false, hello false. So one thing we do have is we're pretty good about unrelated patterns. So you see this, unrelated type will never match string. That's actually wrong. Okay. Unrelated type will never match. Never match bool. So we're saying the right thing, but I think we're mentioning the wrong type here. So if we look at this, the target type is what we should say will never match. Unrelated type will never match string. Yeah, I see what it's saying. Really, so this is the string one. So really what it is unrelated type string, pattern type string will never match. And then this would be the target. So I'll just switch to using my macro here. This is fail. So that's fail span here, and self.type ID to string target type ID. So what we should now see is unrelated pattern type string will never match bool, which is what we wanted. So we could go ahead and there's a lot more of these. I think the rest are a little bit cleaner. So pattern type bool. I think I want to copy this in because the only thing that's going to change is actually that one. Since I'm clobbering my paste buffer, I have to keep doing this. Pattern type char. Pattern int bool. Okay, pattern type char. Pattern type int. Type bool, pattern type char, pattern type int, and we're gonna fix all this formatting with a save, so don't you worry about that. Unrelated pattern type unit. So of course we could dry this up, but it's just really not worth it because things change so much. Pattern type, none. All right. So what is the idea behind exhaustive pattern matching? Well, there's this, there's a famous article, I think. I Googled it a little. I was starting to just implement it kind of naively. Let me show you. Exhaustiveness checking. And here I put some notes from after I read the article, but from before, this is kind of what I had. I had like, okay, so let mutably unhandled cases, and that's going to be match on the target expression. And if it's unit, then the unhandled cases is unit, right? And if it's character, I wasn't handling the, these types. Okay, if it's a bool, then the unhandled cases that we initialize with are true, false. So this is like initialization, right? And then some and none for optional. These are your cases. Of course, this one's very different because this one has an inner pattern, or it can. So the idea was to initialize this unhandled case piece of state and now walk through the typed cases that we've done. So each match arm, each case that is handled, and depending on which one it is, eliminate, if it matches one of our unhandled cases, eliminate it from unhandled cases. And then at the end, if unhandled cases is non-empty, then we have unhandled cases. And this is pretty much what we're going to do, but I think that this approach kind of struggles to recurse. Really, it's not enough to just look at the outermost type. We actually need to sort of build, we need to recurse inside and build, a much richer, like almost like a labyrinth or a maze of unhandled cases. Like if we have a sum of a struct, and then for each pattern, for each field inside the struct. But anyway, it's roughly this. So if you read the paper, which I haven't read any formal CS stuff in like a decade. So although this was published kind of around when I was reading that stuff, but basically, he spends a lot of time talking a lot of nonsense, and then it's been a few months since I read this, but we get to some examples where we see a pattern matrix, which is nice. He sort of defines this relation of what it means for a vector of patterns to match. And then he starts to talk about distinguishing between useful and useless clauses. So row number I, and that is your rows are these, your patterns, your cases that you're handling are rows. So he says row number I in P is useless if and only if there does not exist a value vector V that matches row number I in the sense of definition 2. And definition 2 is essentially, well, let's see if we can find it. Is this definition 2? I suppose so. Let me read right above that, though. Exhaustiveness. Let P be a pattern matrix. Matrix P is exhaustive if and only if for all value vectors of the appropriate type there exists a row in P that filters V in the sense of definition 2. So the algorithm is essentially an iterative one where we generate sort of fake value vectors or inputs, as he calls them. So in our case for bool, the two value vectors we would generate are true and false. And we do that structurally, kind of like I was starting to do here. And then we actually send them through our pattern labyrinth. And then every time a pattern catches one of our value vectors, we remember that. So you can imagine each of these kind of keeps a score, right? So, 1 point for this pattern once he matches false, 1 point for this pattern once he matches true. And now we go through and we say, hey, were any of these useless? And if any of them don't have any points, because they never eliminated a pattern. And that's why the algorithm kind of works for stuff like this, because you walk through and you'd say, hey, this one's redundant. So you can kind of declare patterns redundant is what ends up happening. But the takeaway from the paper, my takeaway was that the best algorithm for doing this is just that, an iterative one where we generate inputs, send them through the patterns, and see if any leak through. If any leak through, that's an unhandled case, and then we already have a witness. We already have one of the things you want to show the user with this is you want to show them what input would have made it through their pattern, and that's exactly what you get when you do this algorithm for free. So that's what we're going to try to do. So let's start with an unhandled Boolean case. And I'm in the middle of a function called evaluate match arms. So I already have my cases. These are so a pattern and an expression. This would be a pattern and then an expression. So those are my cases. I'm in a match scope. I have my target expression, so that's this. I now know its type. And we have, what have we just done? For each of our cases, oh yes, so this is just parsed stuff. So we've actually just evaluated the patterns now. And then a few months ago, I thought that this would be the right place to do exhaustiveness checking. So I'm gonna go with that and believe that it is. And then we will probably end up pulling this out into a function, even though this is the end of this. So this may be the exact right case. You may just pull it out into a function just for the ability to sort of name that whole chunk of code. But let's go ahead and give this a try. Let's just do a Boolean pattern and then maybe one with an inner type. So we've laid out a scaffold. Maybe we'll do option Boolean and Boolean. And if that works, let's see, we're at 15 minutes. So we will have a pretty nice scaffold for continuing next time. So I might talk a little less as I kind of formulate the code in my head. I haven't actually sketched this out yet. So, I don't have any code that says whether an expression is handled by a pattern. I only have, just as a side effect of type checking them, that they're unrelated types. So for the expression, true. And the pattern, true. I need a predicate for basically handles. And I'm wondering if this is going to be repeating some work from this evaluate pattern that we already do, where, yeah, this function doesn't actually do that much work. We start with a literal unit pattern, we finish with a literal unit pattern. All it really does is check for unrelated types. It does a lot more work with enums, maybe? Here's an enum pattern. It looks a lot like an enum. All right. I think we start with this idea of matches. So I say I don't even know if a pattern matches an expression. So how in the world does pattern matching work? Well, I have it at the expression level. I actually, for even more complex patterns, I don't know. Enum, exhaustive. Oh, looks like I had this laying around. But for much more complex patterns, this code works basically. And this desugars to the actual code that it's just a bunch of if else's, really. It's a bunch of conditions checking that the pattern matches. And so that's the actual, at the execution level, I know if a pattern matches an expression or really a value, but I don't know it at the type level, if that makes sense. Sort of at the semantic level that we're talking about here, enough to say that this is handled or not. The only way I can do it right now is actually run the program and see if we get a match error. And the whole point is to avoid that. Okay, sorry for the jumping around. So the question is to represent our value vectors. How to represent value vectors. KA, like input expressions. So for us, this will be true and false. I could just use expression. So I have this. wonderful enum representing every possible expression in my language, and I think I could just use it, and I could just synthesize these things with fake spans, basically make fake expressions. I think that might work pretty nicely. If I'm not doing that, then I have to make an enum that looks a whole lot like this, but just a little bit different, that really only talks about the shape of these things. So it's feeling like a lot of work already. Because I do have so many types. Now, a lot of these are obviously aren't values. Like function call is not a pattern. No, they are values. There's no corresponding pattern. The shapes of things in the language really are optionals, enums, structs, arrays, which I'm not going to do matching on, references, and then all the literals. So let's say we're going to just synthesize expressions. So we'd be like let value vectors equal. So this will be self dot. I want to use language like a gauntlet and like running a gauntlet. So these are our, our runners or whatever. Or our trial expressions. It'd be like our trial expressions, because basically we're going to be sending trials through this pattern, through this sequence of gates. So this will be synth. This will be generate. I use synth for like generating real code. So this will be generate pattern expressions for target type. I find it hard to believe I don't have a target type. Target expert.type ID. Oh, right, I have it as a variable. Okay. So this would be backup typed expert for now. It's the idea of what I want this up with. And then we're going to do for pattern in typed cases. Better pattern. Really, I just care about the pattern. And then, yeah, this is now used. We say if matches, pattern matches, for trial expert and trial expressions. I know you can do this. This confused me a lot when learning Rust. The fact that this lets you iterate. I really like just calling the function that returns the iterator. And then it's easier to call iter mute or to do something else. Yeah, that's why I'm typing iter. Clippy doesn't complain, so I think we're okay. Clippy is pretty strict about those types of things, isn't he? This is a little obsessive. The width capacity, but it just feels so nice to know that that's only going to allocate once. Sorry for the snacking, but I think late night pattern matching checking requires Reese's. Okay. Oh. How do I fill this? How do I... I'm trying to initialize them all to 0 so that I can increment. It's not fill. All right. Rust initialize vector of length and with value expert repeated. Oh, I can do that with, okay. I was thinking for some reason that had to be constant, but I think that's just because it looks like the slice syntax. I don't like that this has to be a, I guess I know why, because the expert gets evaluated once. So that's why it helps. No, I don't know. Evaluated many times because it's a macro? Or why can't this just be a method? That's what I'm asking. I'm not sure. But this is going to be 0, and then the length is going to be sorry for moving so slow and typing so horribly. And then also, what we want to do is keep track of which expressions if a pattern matches, then that expression is dead. So we're going to say alive, and that is true. Child expert alive. This may be overkill because I have the expression as mutable. Can I do this? It's a ref mute bool. Feels like C. Okay. I think this is the algorithm. So let's do this. Match self types. Get type ID type bool. This is where we're gonna fake some data. See, we have to just fake the span. There's gonna be a lot of stuff on these typed expressions that we're going to just put garbage in. Okay, so it's weird to have to return the bools because they're all going to be alive to start with. So we'll fix that later. And now we'll do type optional. Like I said, optional is a good case because it contains a type inside it. So if we're going to have to recurse here, and that's really good. So the patterns, we're going to start with optional none. Optional literal. Okay, I see some, I see get. I don't see optional none. None. Okay, let's rename that. Yeah, that's a pretty clear rename since we have optional sum, optional has value, and optional get. So this is gonna be an optional none. It's gonna be a none of this type. We don't really even need to populate this because I don't think this will be used. Really, all we're interested in is the shape of these things. And then that's gonna be a span ID none, of course. So what I wanna say is none goes in here. And then there's gonna be a sum pattern. And this needs an expression inside it. So inner. And that's going to be self.generate pattern expressions for the type inside the option. Optional type dot inner type. And this is where, and the type ID here, optional sum of, yep, type ID. Hopefully this will indent soon. Yeah, so we can. So there's a sum and a none pattern, right? But notably the sum recurses. So, you know, imagine we have our match opt bool. So we have an option. That's what we're matching on. So we have a pattern for none, and then we have a pattern for sum. And if I wildcard here, I'm done. So there are two cases. But inside here, there are as many patterns as there are the type inside the option. Some false, some true. In this, we'll go ahead and do sum plus. Okay. For now, we'll just match bool. We don't have to call that function. We just have to compile it because everything we need to do that pattern matching is here. We don't learn anything new by calling this. It's not like we've got type parameters or anything like that. Okay, so this is just going to be these patterns. Oh yeah, so what's going on here? So optional sum. Yeah, so this is where abusing my thing doesn't work because we need to be able to express that there could be many patterns inside here, and we can't because this returns a vec. And in our case, it's going to have true and false, and we can't really model that. So we have to start doing. Oh, can we just use patterns? So this is pretty close. It represents the shape better. All right. Sorry for jumping around. Okay. So what I'm thinking, if this returns just typed patterns, the tricky part then will be writing our other function that we stubbed out. This probably should be used. I don't think this used to be unused. Okay. Pattern matches. Because then we're just going to be passing a pattern and a pattern. So what I'm sending through here are actually patterns. So I could send none, I could send some. I mean, that's kind of right, because what we're trying to generate is a pattern, a witness pattern that wouldn't match. Yeah. I think that's exactly what we're sending through here. I think it's all patterns. So these are actually trial patterns. We'll rename them once we're confident this is true. So we still have to fake spans because I put spans on my typed pattern so that I can point to the source. That is too funny. Typed pattern. Literal none. No type on there. Literal. Yeah, it's not literal sum, it's sum. And this is going to be a typed sum pattern. And what does a typed sum pattern have? An optional type ID. Okay. I think that's not going to be used by us in this case, but that's okay. We can have that. We can fake that. An inner pattern. Oh no. Okay, no, two sum patterns. So I could have done this with expressions, because what I want to do is I want to generate two sum patterns. It's actually pretty obvious just looking at this. There's not one sum pattern. Conceptually, there's one, but there's two sum patterns. So we didn't need to go this route. And this is really... Oh, but there are as many as there are shapes of the inner type. So we can't hard code this to bool, and we're not going to do that. And that's going to make sure. What I wanted to do is make an example where we pass like a try type. So type try state enum yes, no, or unknown. Okay, so if we had a type like this, when t I think I need the dot. I'm not sure if I need the dot. I think you get the idea. So we have three. We have as many as there were here. And if yes had a payload, unknown has, this is all valid code in the source language, by the way. So if unknown had a reason, then now we have as many unknown patterns as there are patterns for a string. So hopefully we can get this program working by the end. We got 40 minutes. Okay. Good time to wrap. It would be nice to compile the code though. So this is going to be some patterns going to be, so look, we have the inner patterns, and that's this. We have to recurse. And we're going to do inner patterns map. Actually, we shouldn't use none for the spans. We should just use a span ID that's given to us. In that way, if we do error anywhere here, or if we end up needing to point to this fake pattern, we can just point straight to the part of the source code that we're checking. So we might as well just use the span ID we've been given. Hey, I'm passing 2 now. Okay, and we're missing match arms. So this is going to be what's the most efficient way to do this? Can I extend it with an iterator? I want to do a single vec allocation. For now, we'll do this. Fix me single allocation once. Length is no. That won't be too bad. Oh yeah, I hate this because I don't like this. I don't like it. I don't like it. Fix me. Oh, we should own these. Yeah. We do own them. All right. Yeah. To do unhandled match type. So that all our programs that do pattern matching don't break. In the meantime, we will just yell. Okay. That's generate pattern expressions. And now let's do pattern matches, which is going to be a ridiculously symmetrical looking. By the way, let mute lives. Trial lives. Yeah. Don't do this. This is not. There's a much better way to keep track of this state. We just don't make a Vecca bool. There's almost always a better choice. Is this wrong? No, it's fine. Okay. Span. Span. What span have we been using? Arm expert, match cases, target expert. Match. Sure, we'll do the span of the target expression. Right. It's typed pattern. We switched. Whoa. Trial patterns. Generate trial patterns. For type. For trial expert. Iter. Trial alives. Trial index. Okay, and we're here. I don't need to own either of you. And this is gonna be like match pattern. Okay, so which one is which? If that's the trial, then yeah, so does this pattern match this trial pattern? Yeah, that's right. So typed pattern, throw a bool. True? Then it matches. If we have a false. And with our trial expert, the trial expert will never be a wild card, right? But the pattern could be a wild card. So like obviously the span ID, yeah. Wild card matches anything. And then bools match the correct bool. Yeah, right. None. So none matches none. We just start writing it, and if it gets embarrassing, then, and we know, like so embarrassing that we don't need to write it, and then we'll write the thing that it should be instead. But I feel like it's going to get interesting once we are doing recursive. So at. So the only thing that a sum would match is a sum or wildcard. No, the only thing that a sum would match is a sum. Trial pattern. Oh. Okay, that's cargo check. Let's run this. All right, it got to 50 minutes. I'm sorry. Let's see what we got. What do we even have in here? We're just running match bool, but we have all this stuff in here. So let's comment out our tri-state. But let's keep our optional bool and match ops bool since we did implement those. Okay. Hello, exhaustiveness. False, false. So that's fine. I think some stuff might have happened. Exhaustiveness results. Trial alives. Pattern scores. And we're going to have to decode this. Like zip it up in our heads. So we get trial alives. False, false, false. So that would mean they all got handled. The first one is a true and a false, so one is unhandled. The first pattern handled one case. Each pattern handled one case. So on the 111 here, let's add a redundant pattern. And we'll hope to see 112. And for this one, what we can say is if let some alive index trial alives find one that's alive. Println pattern escaped. Pattern is alive. Pattern made it through. Trial patterns alive index. And for these unhandled, I do want to know. This is pattern trial expert, which is actually trial pattern. And we run this. All right. Find. You guys know what I'm looking for. Ah, yes, it is position. So our actual program prints out false, false. And we did pass 2 falses. Unhandle is alive. What? Oh. One, 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 one. So we're not stopping. So if a pattern matches, then we have to stop. Otherwise, we're going to count everyone's. So we need to continue. I want to continue. 've never used this before. One, 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 zero. Sorry, not 112. 1110. So that would be our. So that's already ground to log useless pattern. This one. And all cases are handled. Pattern made it through, literal bool true. Let's flip it around. True, println true. This is going to match error, but what we care about is the error. Match error at runtime. We have pattern made it through, literal bool false. And so what we could say, pattern made, and say this would actually be return. And now we have exhaustiveness checking for booleans and options. That went well. I'm really happy about this. I'm gonna ruin it. No, I can't. I don't think I even support double nested options, and it's not at the language level. I think it would all work fine. It's actually the postfix syntax will not continue to search for multiple postfix operators. Maybe that's not true anymore. Anyway, I think it depends on the operator. Thanks for watching. I think that's a really neat little start to this. I think next, once we do structs and enums, these user-defined types that have structure to them and shape, it'll be really clear how you would implement this in pretty much any language. And then we have to do the rest of the literals and think through some edge cases, and we have to think through some things like where the pattern is a certain string. Like we can say you've already handled the string, you just haven't handled the rest of them. The same thing if we ever did like pattern ranges like Rust does, where we would something like this, you can get deeper, but I think it's the exact same process. You basically just have this list of trial patterns that you're walking through, and I think you would generate specific trial patterns. So if we knew we were matching on something that where some of the arms contained a specific string or a specific like range of integers, then we would generate trial patterns specifically around that to try and get through it. Because obviously the type of all strings is infinite, so we can't generate a string for every possible string and see if they match. We have to be a little bit smarter. But you know, Rust and other languages already do it, so I think you can also handle those cases as well. But yeah, thank you for watching. See you next time, where hopefully we'll implement the rest of it. Thanks.